When it comes to our daily lives, gravity is perhaps one of the most familiar forces to all of us. It's basically what keeps your feet on the ground and what makes an apple fall from a tree. But for astronomers and for cosmologists, gravity is also a bit of a mystery. Because for cosmology, it's also an invisible architect that seems to build everything in the entire universe and seems to involve everything from the smallest stars to the largest superclusters and massive galactic structures. But also for a very long time, when it comes to actual observations, a few things did not really add up. Or basically, when looking at the entire universe and even looking at individual galaxies, some things still don't really make a lot of sense. Which is why over the years, astronomers propose ideas like the dark matter to try to explain some of these concepts. And that's because here, when we look at, for example, how fast stars move in galaxies, or how galactic clusters move through space, in many cases, they actually seem to move just a little bit too quick for the amount of visible matter they contain. And so there are quite a lot of mismatches between what's predicted and what's actually observed. And so this unusual mismatch eventually led cosmologists and astronomers to start proposing potential explanations, with I guess at least two explanations right now being accepted the most. Either the universe is filled with massive amounts of some kind of an invisible dark matter, something that seems to provide this extra pull, and something that seems to represent 75% of all matter, or alternatively, maybe it's actually the gravity that we don't really understand, and maybe the equations for gravity, going all the way back to Newton, have to be changed and have to be reworked, especially when we're talking about extremely large distances. And so, hello wonderful person, this is Anton, and well, today we're going to discuss this extremely recent study, the study that as always you can find in the description, that basically provides us with the largest scale test of gravity to date. And here it does this by using a very clever trick involving the oldest light in the universe, the cosmic microwave background. And, well, the results from the study seem to give us a pretty certain conclusion on how the gravity works in the universe and what the most likely answer seems to be. And so let's discuss the study and the results in a little bit more detail. But before we start, just a super brief history of how scientists started to learn about all of this and where we are today. And actually, let's go back a few thousand years, all the way to the ancient Greece. And so here, ancient Greek philosophers like Aristotle believed that things fell simply because it was their nature. Or essentially, it was their nature to seek the center of the earth. And yeah, by the way, even back then, the ancients knew that earth was round. But it wasn't until the 16th and the 17th century that we finally began to understand gravity as a universal law. And so first, Galileo showed us that all objects seem to fall at the same rate, regardless of their weight. In other words, he was able to demonstrate that gravity seems to be kind of universal, at least for our own planet. Then, Sir Isaac Newton unified everything. He realized that the same force pulling the apple is actually what keeps the moon in orbit as well. And he basically was able to apply this to all astronomical objects and even find a way to calculate pretty much everything. Newton gave us the inverse square law. This is a simple but powerful rule that tells us that if you double the distance between two objects, the gravitational pull between them decreases by 4 times. So basically here we're talking about 2 squared. And this rule worked perfectly for the entire solar system. Every single planet away from the sun felt a lot less gravity the more distant from the sun it was. But as our telescopes got better and better, we also started to notice very small glitches, with the most famous glitch being around Mercury. For some reason, Mercury, being the closest to the sun and having the shortest orbit and also moving at the fastest speed, was surprisingly not orbiting with the exact precision it was expected to orbit. In other words, its orbit did not match Newtonian predictions. And that's where Albert Einstein came in and by 1915 was able to work out exactly what's happening. This was the birth of general relativity. Here, he was able to describe gravity not as a force or as a pull, but basically as the curvature of space-time itself. The very fabric of space-time that would be affected by massive objects. And so here, because of the sun, the space-time was curved in such a way that it didn't just make Mercury orbit around it, it also created a tiny dilation effect that gave it a lot more precision than what was expected based on Newtonian formula. And so Einsteinian rules gave us the precision needed to understand the much wider universe and of course much more massive objects like neutron stars and black holes. But for everyday life, Newtonian physics still obviously worked. Except that in the 1970s, additional observations from astronomers like Vera Rubin once again noticed something that was kind of unexpected. For some reason, stars at the outer edges of spiral galaxies, like the Andromeda, seem to be orbiting much faster than expected. And we're not talking about like 1 or 2% faster. We're talking about hundreds of kilometers per second faster than what Newtonian physics predicted. And that meant that when it came to galaxies, Newtonian rules no longer worked. There was just not enough visible mass to hold the galaxy together, and all of these stars should have already escaped the galaxy into outer space. Which is where we got these two new propositions. The first, and the most widely accepted, is the idea known as dark matter. The proposition that there is a lot of this invisible substance, whose nature is currently unknown, that doesn't really emit any light and doesn't reflect anything, but interacts with things through gravity only. And so basically it acts as a kind of a gravitational scaffold that holds galaxies together. But there's also another idea referred to as MOND, or modified Newtonian dynamics, which suggests that there are no particles and no additional matter, but instead gravity just might get a boost at extremely low accelerations, especially at distances far away from the center. And so basically in this case it's actually the Newtonian formula that are being rewritten, which is why it's called modified Newtonian dynamics, in order to then explain why those distant stars move so fast and why the galaxies do not fall apart. Now, we've discussed both models in some of the previous videos in the description, but in a nutshell, over the years, the MOND proposition has unfortunately been more or less disproven. And though some scientists are still continuously researching it and are trying to find some evidence, this idea of changing Newtonian formula seems to not actually make a lot of sense for many different larger objects such as galactic clusters. But this also now brings us to this recent work by Patricio Gallardo and a large team of international researchers, because in this case they wanted to see if maybe MOND might make sense if we look at even larger structures and the entire universe as a whole, or if maybe the Newtonian models are correct and the dark matter proposition makes more sense. And so basically, just to rephrase this, they wanted to see if Newtonian's inverse square law still holds up over much larger distances. Here we're talking about hundreds of millions of light years, involving scales that would actually be inconceivable to Newton himself. And to do this, they used ACT, Atacama Cosmology Telescope in Chile, that doesn't actually look at stars and instead looks at the cosmic microwave background. The faint afterglow, or the oldest light in the universe, that basically appeared when the universe cooled down and when some of the first light was able to finally pass through after about 380,000 years following the Big Bang. Now this is the light we've been studying for an extremely long time, but in this case they wanted to actually see specific deviations by looking at something referred to as KSZ, or kinematic Sunyaev-Zeldovich effect. Now, for those of you who want to find out what exactly this is, the link from Caltech explains this in a lot of detail, and you can find it in the description. But in a nutshell, this is the effect that acts on this ancient light as it tends to pass through massive galactic clusters or any structure containing a lot of matter. And that's because as the light travels through this, some of the electrons in the matter actually give the light a bit of a kick, very often increasing its energy just a little bit. And then by measuring these very tiny changes in light across hundreds of thousands of galactic clusters, and by essentially comparing this across the universe, scientists can calculate exactly how fast some of these clusters are being pulled toward each other, and thus calculate gravitational effects and overall gravitational interactions. And by tracking pairs of massive halos, which are essentially dark matter structures containing galactic clusters, but in this case involving very large distances of several 100 million light years, here they were able to test the gravity law directly. Now remember, the Newton's rule is that the gravity weakens by the square of the distance. And so in scientific terms, it means that the power law index, which we call n, should be exactly 2. And if the theories like MOND or other explanations involving modification of formula were correct, we would actually expect to see a kind of a flatter or a kind of a drop, where n should be closer to 1. Or basically we would see that over these distances, the Newtonian law is not actually accurate, and it's not really the square of a distance, but something much smaller. But the results seem to indicate the opposite. Here, all of the results were super clear, and they found that n seems to equal 2.1 plus minus 0.3. So basically, extremely close to 2 with a very small error, which is what you're seeing in this graph. And this is of course a huge deal. It basically confirms that even across extremely vast distances, and even involving empty voids and massive galactic structures, gravity still follows the rule set out by Newton and Einstein. With this data almost definitively closing the door on all of the other propositions that try to explain cosmic motion by modifying the laws of gravity or by changing Newtonian formula. So once again, Mond unfortunately cannot explain this and completely fails to explain anything. And though even the lambda CDM model or the dark matter dark energy model that we use today does not fit perfectly yet, it's definitely a much better explanation at this point. And this directly reinforces fundamental pillars of modern cosmology by using a completely different independent observation involving something entirely different and not just galaxies or motion of stars. But more importantly, this also definitively shows us that gravity is also constant. It has not changed for a very long time, and gravitational constant potentially remain constant for at least several billion years. And so in this case, this missing mass problem cannot be fixed by modifying equations, and the solution has to lie somewhere else. And though this obviously strengthens the case for the existence of some kind of a dark matter particle, even that is obviously still a mystery. No such particle as of 2026 has been found anywhere. It still seems to be kind of invisible, despite providing all of this extra pull. But even as researchers themselves put it, while we are more certain than ever that dark matter seems to be there, the next big challenge is figuring out what it's made out of. Now in the past, scientists believed it was some kind of a massive particle referred to as a WIMP, but that also has now been almost entirely disproven. It could be something referred to as an axion we've discussed in one of the previous videos, but that's kind of difficult to prove as well, mostly because they would be extremely small. But maybe Stephen Hawking was correct, and maybe it's all microscopic black holes. You can learn about that concept in one of the previous videos. But in a nutshell, this study based on the KSZ effect also shows us that this is an extremely powerful new tool. A tool that we can now use to test a lot of other propositions and to study cosmology in ways that was previously extremely difficult. And so here scientists can now start testing additional laws and possibly rule out other alternative propositions with even higher certainty. But here it's also kind of remarkable that a law proposed in 17th century by Newton and Galileo, and that was mostly used to describe falling objects, still holds its ground in the 21st century across the entire observable universe. Which means that gravity remains one of the most fascinating, or technically one of the most naturally attractive fields of study in science. But until we find out something else, that's all I wanted to mention. Check out all the links in the description. Thank you for watching, subscribe, come back tomorrow to learn something else. Support this channel on Patreon where you can find additional videos without any ads and can DM it directly, or by joining a channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.